And in Neurosymbolic AI, what we try to do is to find a midway, to find, let's say, a way of combine these two schools. And in Neurosymbolic AI, what we do is we learn from the experience, okay, from the data we gather from the environment. We can imagine, for instance, a robot that is equipped with sensors and gather visual information from the environment. And we combine this with the ability to reason about what was learned. We can think in terms of, okay, educating a child. This is my daughter when she was quite young. She realized that she could apply the same procedure that we applied, let's say, in brushing her teeth. She realized that that was possible to learn, let's say, from the environment and apply the same procedure over her toy, right? So the motivation here is to learn from changes in the environment. The environment is, of course, very dynamic. And when you are learning from the environment, you have to think not only in terms of classical reasoning. In terms of classical reasoning, you have some simple propositions that you can represent in the proper way at the right level of abstraction. But when you think in terms of moving around an environment, you have to reason about different dimensions. For instance, space, for instance, time, for instance, uncertainty. The environment can be probabilistic. When you are crossing a street in a large town, you have to pay attention to several actors moving around. You have to pay attention to cars, and you are dealing with probabilities. When you want to cross the street, you make some mental calculations. Well, okay, what's the likelihood that I'm going to cross the street and I will have not a problem with a car that's coming about? Okay, so this is the complexity that we have to deal in artificial intelligence. We have way too many dimensions to use only one single technique that fits it all. So in the end of the day, we're trying to integrate reasoning that we associate with computation in computer science and learning. So we are combining the logical nature of reasoning and the statistical nature of learning that deals with uncertainty, that deals with a lot of data. But as we know, reasoning can be complex, reasoning can be extremely hard in computer science. And there are several approaches that deal with this problem. The approaches are motivated by several reasons. One of them is to explain. Other approaches are used to understand and to reason about open, complex environments. Other approaches try to use there's several approaches using different techniques to tackle this problem. For instance, one of the approaches is known as logical neural networks, is an approach that has been developed by the IBM research lab in the US and in other sites. They do some representation of classical reasoning and some representation of relational reasoning and predicate first order reasoning. It's a very efficient application to certain domains. Our recent approach is to understand how Boolean function learnability can be processed in deep neural networks. This approach is inspired by the theory of pack learning. We're trying to understand actually what are the limits of deep learning. This is one of the approaches that is currently under development. Another approach was put forward by a group of Italian researchers, including Marco Gori. Marco Gori is one of the pioneers of graph neural networks that are quite popular these days for a number of applications. And their motivation was actually to build networks that are explainable by construction. So given a certain way of building the deep neural networks for machine learning, given some assumptions that you take, you can, by construction, build neural networks that are explained. Other approaches combine, for instance, techniques from inductive logic programming. Inductive logic programming has been developed over the last 35 years, also to combine the power of logic programming and relational learning, relational reasoning. And some recent work combines both approaches. How can we integrate, let's say, inductive logic programming in a neurosymbolic way where logical neural networks, that's the framework developed by IBM, can do, let's say, the reasoning procedures and the learning procedures using some representation using an inductive logic programming technique. And finally, there is an approach that was developed by a group of friends here, some Arthur Garces and Luciano Serafini, and some researchers from Sony in Japan. That's called logic tensor networks, where they use tensor capabilities of very effective learning combined with a fuzzy representation, let's say a fuzzy logic-like representation of relations into a neural setting using the typical techniques that we have in deep learning by using tensor algebra.